This class notes at the end of it, most of these slides are there. Okay, so in case those of you who actually look at the slides while I'm talking, you can do it that way. But after the class, I will put them on. Okay, so before I start, are there any questions? Okay, so we have talked about propositional logic, and it was sort of useful. And today we, segue from there. We leave that and get into probabilistic propositional logic. And to do that, before we do that, let's kind of do a very short review of what we could and could not do with propositional logic. Okay, so basically, in propositional logic, if you have some knowledge, you can write it as propositional axioms. Okay. So you want to write what you know as propositional formulas, and then the theorem proving will then tell you whether certain given sentence will hold given what you already know. That was like the big contribution of propositional logic. Okay, and we noticed that theorem proving and satisfiability are the yin and yang, and in fact, in using satisfiability, you can do theorem proving. In trying to do satisfiability search, you can do theorem proving and prove to yourself that the current partial assignment won't work. Okay, and similarly, if you have a systematic satisfiability solver, then you can use it to show that the knowledge base plus the negation of what you're trying to prove would be an unsatisfiable theory. In which case, you better believe alpha is true, right? So those are the things that we learned. By the way, I don't know whether this is obvious to you guys or not, but what I do when I go back from the class and when I put in the lecture notes, I write what I think actually happened in that class. Okay, at the minimum, if you are supposedly preparing for a midterm or something, you should know all those things. That's your cheat sheet, really. Okay, and if you go back to my previous exam and see if there's anything that I asked that was not there in one of those, you'll be surprised that most of the important points that came up in each lecture, I throw them in there. Okay. Okay, so we know all that about the theorem proving and satisfiability. And then in general, in propositional logic, what I'm trying to focus on today is what kinds of questions can I ask? What kinds of questions can I ask? Okay, to propositional logic. And to some extent, we'll see interesting an interesting scenario where you would be interested in asking questions that propositional logic can't support. Okay, before we get there, we'll essentially want to know what kinds of queries can you do in propositional logic. One question you can ask is, so I know something about the world, is my knowledge consistent? Okay, your knowledge is consistent if it at least has one model. Right? That means there's some world in which all of what you know is true. Okay, if there's no world in which all of what you know is true, that means what you know is inconsistent. Okay, so the question of is my knowledge base inconsistent is really, is my knowledge base satisfiable? Or does it have at least one model? Okay, the other kind of questions I might ask is this is a standard question. Is a particular sentence entailed by my knowledge base? Given what I know, can I prove that S follows? This is a standard one. This, we had it in the back of our head, but sometimes you want to check consistency. And the third is the sentence S consistent with my knowledge base? So the idea is, if you let your knowledge base go all the way to 0 models, it's too late. Okay, as you are gaining knowledge, you need to ask yourself if the next bit of information I'm about to give you is going to break your knowledge base by making it inconsistent. If so, you say, don't tell me this, because what you're telling me is going to be inconsistent with what I know. So either I have to forget something that I know, or you don't tell me what you're about to tell me. Do you see what I'm saying? Okay, so apart from asking, is the sentence S entailed by my knowledge base, I might also ask, is the sentence S consistent with my knowledge base? S is consistent with the knowledge base, okay? That base, so if in fact S is true in at least one of the models of the knowledge base. Or alternately, if not S is entailed, then I better not tell you S. Okay, given what you know, if not S is entailed, then if I throw in S, then you will be dead. Okay, so those are the three kinds of questions. I mean, you probably thought about this already. This is also an interesting question. This is also an interesting question. All of these are supported by propositional logic and the same mechanisms that you have. Okay, so as I said, S is consistent with the knowledge base if not S is not entailed by the knowledge base. Not S is not entailed by the knowledge base. If not S is entailed, then S is not consistent with the knowledge base. Okay? Now, so that's about propositional logic. So let's start talking about a scenario. For reasons that become clearer, this is the scenario I'm interested in. Some guy called Pearl lives in Los Angeles. Okay? And it's in the place where his house is. It's a high crime area. So Pearl installed a burglar alarm in his home. He asked his neighbors, John and Mary, to call him if they hear the alarm. Okay, this way he can come home if there's a burglary, basically. And then I guess that all his stuff is gone. Los Angeles is also earthquake prone. When there's an earthquake, that sort of sets off burglary alarms too. Okay? Alarm goes off basically when there is an earthquake. Alarm also goes off when there is a burglar. If there's an alarm, then John and Mary will call Pearl. Right? This is my scenario. So can I write this down? Of course. Burglary implies alarm. B implies A. These are my propositional symbols. Earthquake implies alarm. Alarm implies John calls. Alarm implies Mary calls. That's my theory right now. Okay? So what kinds of questions can I ask? For example, here is a question I can ask. If there is a burglary, will Mary call? Given my knowledge base, if there is a burglary, will Mary call? Because B would imply A, and A will imply Mary calls, so you will say, yes, Mary will call. Okay. If Mary didn't call, is it possible that burglary occurred? If Mary didn't call, is it possible that burglary occurred? Okay, so I would then say not Mary call. If this not Mary call, then means not alarm. Not alarm means not burglary. Very interesting questions. Right, we could do this. And if you have a propositional theorem proof, it will also answer all these kinds of questions. Right? That's up to here, well and good. Now, there's nothing wrong with this example, except it's not completely realistic. To the extent any example can be realistic, you can make this more realistic by throwing in some extra characteristics of the real world. So the scenario still holds, except Pearl is living in real Los Angeles, in real world, where one, burglars can sometimes disable alarms. So just because there is a burglary doesn't mean alarm will go off. Okay. Two, some earthquakes may be too slight to cause an alarm. Three, even in Los Angeles, burglaries are more likely than earthquakes. Okay. Four, John and Mary both have their own lives and may not always call when alarm goes off. Five, between John and Mary, John is more of a slacker than Mary. So in fact, when the burglary alarm is going off, John might be just having his beer, whereas Mary will actually go and call. Okay. Six, John and Mary may call even without alarm going off. Now, just because as soon as, nowadays all of us have these caller IDs. So, Pearl shouldn't just give up as soon as he sees John or Mary calling, thinking all my stuff is gone now. This is not surprising. In fact, in the old days when telegrams were first came into being, they were mostly used to give notifications about you got Nobel Prize or somebody in your family died. Since most of us don't get Nobel Prizes, if you get telegram, most likely somebody in your family died, right? So even before you open the telegram, you start weeping. Because somebody died, might as well start weeping. And then you'll find that maybe nothing happened. Okay, so essentially, just because John and Mary called doesn't necessarily mean that Pearl should start weeping that all his positions are lost. Maybe they just said, hello, how are you doing? All of these are reasonable, right? Okay, so my question is, obviously this model doesn't capture that. You need to write more to this model. Furthermore, what's more interesting is, given this additional knowledge, I can ask these questions. I can also ask these additional questions. First of all, so this one says, John already called. If Mary also calls, is it more likely that burglary occurred? Use your common sense. What do you think? If John called, okay, you just saw John, there's a missed call from John. You went to a meeting and you came back, there's a missed call from John, and then you go down, there's one more missed call from Mary. So do you now think, when you first saw John called, you sort of thought maybe there's a burglary, okay? And now you see Mary also called. Do you now think there is a higher chance of burglary, a lower chance of burglary, as the same chance of burglary? Higher chance of burglary is what most of us think. Propositional logic cannot capture that. Because if this is your knowledge base, then the moment John called, burglary occurred. Mary calling doesn't add any more. You see what I'm saying? So this plausible reasoning that we do is not captured by propositional logic. And even more interesting is the next question. If you now also hear on the TV that there is an earthquake. So you see John called, you see Mary called, then you put on the TV. I don't know what you are doing at home, at work, but you also have a TV. You put on the TV. You see that there's one more earthquake in Los Angeles. At this point, does your belief that there is a burglary at your home increase or reduce? Reduce. Why? Yeah. Why can't we be in a situation where both earthquake and burglary occurred? Again, plausible reasoning. We assume plausible reasoning. If you have one explanation, you don't need another explanation. This is an idea called explaining away. Right? You essentially now have an explanation as to why the burglary, you have an explanation as to why alarm might have gone off, earthquake. So you don't need one more explanation. In particular, when you have this explanation, your belief in the other explanation reduces. Both are trying to explain this, what happened. To the extent you believe this, you don't need this. Right? Why do we think there is actually a creationist camp and an evolution camp? Why can't we just assume that God invented evolution and then made creation, whatever? Both of them hold. Because you don't need two explanations. Even if you have no clue about science, you don't need two explanations. If you believe in one, you don't need the other. Okay? Once again, propositional logic doesn't capture that. Okay? Because in essence, there is no such thing. If you actually, in fact, notice in this case, you got additional evidence. Previously, in some sense, in a propositional way of speaking, you sort of believed in burglary before hearing about earthquake. So in some sense, you sort of proved that there is a burglary. Once you prove that there is a burglary, no amount of additional evidence can make you disprove burglary in propositional logic. Because you proved it, it's 100% true. So any additional thing cannot reduce your belief in it. So in some sense, actually, this question and your understanding of what happened in this question makes you also realize, with respect to one of the problems that I suggested in the thinking cap, that plausible reasoning is non-monotonic. As evidence keeps flowing in, your belief in burglary goes up and down and up and down and up and down. It doesn't have to just keep going up. Do you see what I'm saying? Okay, so these are aspects, these are some of the aspects that propositional logic doesn't capture. So there are two issues this slide brings up. One, I know this much more about the world. How do I model it? And two, if I were to model it, then I should be able to hopefully support these kinds of inferences. These inferences that you have some understanding, plausible, based on your plausible reasoning capabilities. And whatever your theorem prover says should sort of should sync with that. Okay, so this is one way of, about many, many different ways, this is one way of going from propositional logic to probabilistic logic. Okay, I mean, basically I'm sort of saying that one way of doing this and this is probabilistic logic. But before I go there, I'll still go by steps. So, how do we handle real world? That's basically the question of the day. Okay, so one idea is omniscient and eager way. Omniscient means you know everything, how everything connects to everything, so you write it all down. Okay? First you know it, and second you have the time to write it all down. So one is omniscience, and the other is eagerness. Okay? Let's think of what happens. So model, first of all, you should do everything, and you must model everything. Okay? Now, so basically you want to model exactly the conditions under which John will call. So instead of just saying alarm implies John calls, you want to say alarm and John is feeling like calling and John is not angry at you and he's not drunk and something else implies he will call. Okay, so that means you want to qualify this. Apart from alarm, you want to write a bunch more conditions. C1 and C2, etc. Cn implies J. Okay, the problem, of course, is how many exceptions are there? In a realistic world, you cannot write down all the exceptions. You really cannot write down all the exceptions in a realistic world. Okay, and furthermore, not only are there exceptions, the exceptions can have their own exceptions. Okay, so for example, I might say C1 and C5 would imply not C9. So there is like a theory of exceptions, unexceptioning some of the other exceptions. And how much of this are you going to be able to write? This is actually called the problem of qualification. In any real world, the knowledge you have cannot be completely qualified. You don't know exactly under what conditions a particular implication might hold. Or for example, this is also saying under what conditions would an action work. For example, if you're writing planning actions and you're writing the preconditions of planning actions, what are all the preconditions for an action? Think about the following thing. I want to talk about what conditions must be satisfied such that when I start the car starts. Tell me the conditions. So you switch the car, you put your key and you turn the ignition, the car should start. Under what conditions would it start? Ignition should work. Fuel should be there. Battery should be there. You should have the key. You should have the right key. The police are not looking over you because you are using somebody else's key. What else? You should turn it in the right direction. There should be battery. the 59th wire between the 84th module and 97th module should be actually working, which you did not know until now that they existed, but it should be working. You wrote all this down, and you turned the key. One of the nice things is if all of those have been checked, right, and you turned the key, you shouldn't even have to listen to see whether or not the car is starting. It should have started. I proved to myself that the car started, so I will just act as if I'm driving. Right? Right? So the question is it enough? Have you thought of all possibilities? You have large number of smart people, some of who at least drive, and you came up with some exceptions and that we need to check before key turning will start the car. Did we consider all exceptions? What if you happen to have a potato in the tailpipe? If you have a potato in the tailpipe and you start the car will start, sputter, and stop. And by the way, this is not just for potato. Bananas will work. So do all sorts of various kinds of things. Have you thought about it? No. Now I told you. So now onwards, before you start the car, go behind, check if there is any potato and remove it. And see how many people think you are a smart guy. And you can have this big, the car bumper sticker that says, just because you aren't paranoid doesn't mean they're not out to get you. And just because you're not checking doesn't mean there is no potato there. The point of this, by the way, this potato in the tailpipe is a pretty famous analogy. It is a famous, I don't know what should be called, allegory or analogy, that John McCarthy made up. John McCarthy is a big guy. Why should we care about him? He also made your life miserable. He invented Lisp. He invented time-sharing computing, and he also did a large amount of work in AI. He's considered one of the 4 people who started the field of AI. In fact, he gave the name artificial intelligence to artificial intelligence. Okay, so he's a big guy. He passed away, in fact, last year. Anyway, so McCarthy basically pointed out that you cannot actually write all conditions in any realistic world. You cannot write all the exceptions for any rule. That's why we just say in a plausible reasoning, and this is not surprising to you in real world, right? That's why we say every rule has an exception. And that rule also has an exception, right? And so we don't actually believe that anybody should be foolish enough to say, I'm omniscient. I know all the exceptions. Not only that, I have nothing better to do than writing all the exceptions down for you. And so there are major number of problems in doing it this way. One is, unless it's a toy world, A, you won't know all the exceptions. B, even if you know them, you won't be able to write it. And C, if you write it, you are dead. Because you will never actually drive a car in your life. Because, you go to start the car and about 10 hours later, you're still checking all possible exceptions. Most of which are most of the time not holding. But since you write it, you have to check. Okay, you have to check if there's a potato, there's a banana, there is a, something else, and all sorts of wires, everything. Check everything before you start the car. And assume that the car started. Okay, so this won't work. I hope you understand this. And so it actually goes under 2 names, qualification and ramification problems in AI. A qualification problem essentially says that for any realistic world, you don't quite know what are all the exceptions for a rule. Ramification problem says if J were to become true, you don't quite know what are all the consequences of J becoming true. So basically, you don't know anything. Okay? One other interesting thing about this omniscient and eager way is they said, you may not know all the exceptions, and you may not have the time to write it down, and you may not be able to reason with them. And a fourth one is you may not have memory to store all these exceptions. Okay, lots and lots of entities show intelligent behavior. Ants can show reasonably intelligent behavior. Ants don't have gigabyte memory. You see what I'm saying? How do you get by without having to write all of this? That's an important thing. Okay, so you should understand that this is possible only in toy worlds. Many a time we will hope that our world is toy world and model it that way. Okay, now the second idea, which is not omniscient and not eager, is ignorant and lazy way. So you admit that you're ignorant, and you also admit that you're lazy. I wrote a few things. Then there could be exceptions, and may have forgotten some things, and still you should get by. Okay? So the idea there, one idea is model the likelihood. In some sense, you want to say, if this and this and this hold, generally this holds. You never give certain assertions. You don't give categorical assertions. You say it's likely. This is what you always, it's not surprising to you. I'm just bringing you, into this reasoning from propositional logic, but none of this should be surprising to you. If it is, you wouldn't have been old enough to actually sit here and lived long enough to sit here, because you are doing plausible reasoning every day, right? So model the likelihood, you might be able to say that in 85% of the worlds where there is an alarm, John will actually come. Okay, so this 85% is interesting in the sense that it allows you to capture both your laziness and ignorance. You may not know some of the other things that will stop John from calling. Or you may not have cared like writing down, even though you knew what could stop John from calling. Either which way, if this rule is satisfied, let's say, if this rule is satisfied, John may not still call. He may be only calling 85% of the time. And that's your probabilistic reason. Okay. Now, actually, the interesting thing is, of course, how do you do reasoning with likelihoods? And while we will focus on probability theory and talk about essentially effective methods for dealing with probability theory, you know already probability theory from your elementary mathematics courses. What we will be doing here is how to do it in large scale, how to do the inference. The ones that you did by hand, how to do them faster, on large scale knowledge bases. That's what we'll learn. But before going there, the interesting thing actually in AI is that for a variety of philosophical or biased reasons, people didn't try probability theory first. Okay, anything but probability theory is actually what they tried for the longest time. So in fact, I can show you textbooks on AI which had statements saying, obviously humans don't use numbers in their thinking, and so they don't use probabilistic reasoning, and so we shouldn't be worried about dealing with probabilistic reasoning in AI. So we'll try something else. Okay, there are textbooks on it that were written back in, even as late as, 90, which had this kind of a view. Okay, so then variety of alternatives were invented, some of which, in fact, I list two of them here. One is called the notion of non-monotonic logics, where in essence, what you would like to say is alarm and nothing abnormal implies John calls. Okay, and then this abnormality then should somehow be treated as a different proposition than other propositions. It's not a normal logical proposition. So in particular, one idea is you might say that if I can't prove anything abnormal, I'll assume not abnormal is true. That's not true in logic, right? If you can't prove P, you can't assume not P. But abnormality, for example, you might use this notion of closed world reasoning. You'll assume that, okay, I tried to see if there's anything abnormal. I looked around here and here. There's nothing abnormal, so I'll assume not abnormal. And my rule says alarm and not abnormal implies John calls, so I get to use John calls. Now and then I come and say, hey, did you notice that this is abnormal here? Alarm and John is kind of convulsing in a fit. Okay, that's not normal for John. So clearly, there's abnormality with John right now. So you say, yeah, there is abnormality. So now, obviously, I can't use this rule. So now I will derive that, okay, John won't come. You see what I'm saying? I first proved John called. Then you said, you can't prove that. I said, okay, I would now prove that John won't come. That's non-monotonic. In a propositional logic, you prove something, you are stuck with it forever, whether you like it or not. Okay, so that's sort of an idea of non-monotonic logics. It's like a very small thing. I mean, there's a bigger slide here. I would suggest you read it. For example, if you want to say something about birds flying, you would say birds and not abnormal bird implies flies. And this is my thinking gap example. Okay, then I would say, so if I say Tweety is a bird, you will say, well, since I don't know anything abnormal about Tweety, I'll assume Tweety is a normal bird, it will fly. Then I'll say Tweety is an ostrich, then I say, hey, ostriches are abnormal kinds of birds. Okay, so Tweety is abnormal now, so Tweety doesn't fly. Then I say Tweety is an ostrich, that's magical. Then you say, well, even among abnormal ostriches, this is more abnormal of an ostrich, so it actually can fly. So you keep going back and forth. You allow your mind to change. This notion of flip-flopping is actually good because that's how plausible reasoning works. People who don't flip-flop are either using monotonic logics or just ignore evidence. Okay, I made up my mind, I'm not going to look at the evidence anymore. That's a good way of not ever changing your mind again. Okay? So that's an idea. And this idea is not actually, I cannot say it's technically wrong. Especially because if I were to say, so Chitta Baral and Chuhyung Lee will come and hit me. They are both faculty members here, and they work on this direction. Okay? It's just a question of, it's right now, there's much more people trying the probabilistic reasoning idea. So I will teach that more in the introductory AI course. If you ever take a course with either Chitta or Chuhyung, they will make sure that you will know non-monotonic reasoning, which is an alternative approach. Okay? There's nothing wrong with it. It's just, I think there are some computational issues, and it's also kind of minority view right now. Okay? And there is another idea called certainty factors. The certainty factors idea essentially is, we'll just have these rules and put a number here next to it. Burglary implies alarm 0.9. Earthquake implies alarm 0.7. Alarm implies John calls 0.3. Alarm implies Mary calls 0.7. And you feel kind of warm and fuzzy because you put some numbers on these rules. And you are not still using probability reasoning because that is the stuff that you learned in elementary mathematics. You should not use anything that you learned in elementary mathematics. You should reinvent the wheel, even if it is square-shaped. Right? Now, unfortunately, in fact, when AI systems started using, one of the earliest systems that were using these kinds of rule-based reasoning were these expert systems, okay, which would be developed for any specific domain. So, for example, medical expert systems were very popular at one time. In fact, that's what put AI into big limelight back in 80s, early 80s. Okay, and so when they originally would write basically simple predicate logic, or not propositional logic, but predicate logic rules for the expert systems, and then do rule chaining to come up with answers. And then they realized that you need some sort of uncertainty because rules are always having exceptions. And so they started doing this notion of certainty factors, which is you put a number for each of the rules, saying how likely you think that rule is. Looks nice and good. Unfortunately, it has no clear semantics. In particular, so associate numbers to each of the facts and axioms. when you do derivations, compute the certainty factor of the results. So for example, if I started with a fact and used a rule with 0.7 certainty, and then use another rule with 0.3 certainty, then the fact I derived would be 0.7 times 0.3 certainty. Looks good. You know, the problem, of course, is you can easily get into circular reasoning. So for example, raining implies grass wet. If it's raining, grass becomes wet. If grass is wet, you can assume that it is raining. Right? In medical expert systems, this is very important, right? If you have runny nose, you probably have flu. If you have flu, you'll probably have runny nose. And so I can go into a nice cycle and then, you know, do cyclical reasoning. How do I stop that from happening? What exactly is the semantics of this kind of reasoning? And it turns out, so for example, if you know grass is wet with 0.4, then we know raining, which makes grass more wet, which makes more rain, which makes more grass. I mean, it's just, you know, you don't have to do anything. You know, things are already, you know, going into cyclical reasoning. And essentially, to make it correct semantics, you will have to slowly change the certainty factors into probability theory, which existed already. You just didn't like it because you learned it in the elementary school and you don't want to use it. So we go back to it. Fine. Okay, so again, I'm not going into these two because this one, it's because it's minority view for now. And this one because it's a dumb view. It doesn't work actually. It has no semantics. People still use it, by the way. Okay? There are variety of areas which use this, you know, this notion of certainty factor-based rules. And sometimes it might give reasonable answers, but there is no semantics. You can't be sure that it will always do the right thing. Okay? As long as we are at it, there is one more thing. I wonder if I have the slide for that. Maybe I do. No, I removed it, unfortunately. Yeah, there. Let's just remove the height. I should write that too, which is fuzzy logic. How many of you heard of fuzzy logic? A lot of you, right? Okay, and I did tell you that I'll yell at fuzzy logic in this class, and this is, you know, whenever, you know, I'm basically putting non-monotonic logic, certainty factors, I should put one more bullet called fuzzy logic, and I skip over it, and I go to probability theory, which you already know. Okay, so before we go to this, I kind of, you know, dismiss everything else. So I dismiss two for different reasons, and the third one I'm going to dismiss is fuzzy logics. Okay, so the idea of fuzzy logic essentially is, as I said, it's essentially degree of truth itself. Okay, so you know, this is the picture I was trying to paint in your head at one point of time. If you have a bucket of you know, puppies, some white puppies and some brown puppies, you close your eye and pick a puppy. Okay, you don't quite know what its color is, but you do know that it's either white with 1.0 probability or brown with 1.0 probability. Okay, but on the other hand, if in fact, so what you would like to say is basically, you would ask if it turns out that you actually pick and the color is anywhere between white and brown. Okay, then essentially the truth of a proposition in a word, in a given model itself, is not 1 and 0, but somewhere in between. In propositional logic, the truth of a proposition in any given word is either true or false. That's the same case for probabilistic logic. But in fuzzy logic, it can be, truth itself can be between 1 and 0. Now, the interesting thing is, what fuzzy logic tries to do is, in some sense, it tries to suggest that you can do probabilistic reasoning in a simpler way. And unfortunately, that's what certainty factors also suggest to you, that somehow you don't need to know probability theory. You can just do these numbers for each rule and multiply them. That's what certainty factors said, and it has a problem. Okay, the fuzzy logic rules essentially are each of the variables, each of the propositions have a truth value. Okay, truth value of A can be between 0 and 1. This is not probability. This is truth value of A is between 0 and 1. Okay, and then truth value of not A is defined as 1 minus truth value of A. And truth value of A or B defined as the max of the truth value of A and truth value of B. Okay, and similarly, truth value of A and B is defined as min of the truth value of A and truth value of B. By the way, these rules directly explain propositional logic. If your truth values can only be ones and zeros, right, then A or B is max of truth value of A and truth value of B. This is either 1 or 0, this is either 1 or 0. If both are zeros, you will get 0. If any of them is 1, you will get 1. And similarly, if in this case it's 1 or 0, this is 1 or 0, only when both are 1 would you get 1 out. Because minimum of 1 and 1 is 1. Minimum of 1 and 0 or 0 and 1 will still be 0. So in some sense, fuzzy logic tries to somehow get plausible reasoning by keeping the simplicity of propositional logic and somehow making slightly different rules for this. Now the problem, one of the problems, and you can read this in the textbook again, is it has inconsistencies. The set of rules there wind up having inconsistencies. Why? Okay, why? Because let's say truth value of A is 0.3. Then truth value of not A is 0.7. So truth value of A or not A be 0.7. But how does that make sense? You see what I'm saying? This is like the tip of the iceberg. Obviously, again, it's not like nobody is doing fuzzy logic, right? There's still papers on fuzzy logic. Again, this is a controversial issue. Some people, think, including the textbook that you're using, and I'm also convinced that there are essentially semantic issues with fuzzy logic. Semantic inconsistencies with fuzzy logic. Now of course people say, no, how does that matter? My washing machine is using fuzzy logic. And their dryer is using fuzzy logic. Everything coming out of Japan at one time was using fuzzy logic. And truly, in fact, they had this fuzzy logic thrown into the inference systems for these simple things. And there's a very nice paper that somebody wrote long back titled On the Paradoxical Success of Fuzzy Logic. Okay. And essentially their argument is, as long as you only do shallow inference, that means inference of maybe 1 level or 2 levels, you'll be okay. If you do deep inference, then you can get into circularity problems. That's sort of true also for the certainty factors, right? If I only use this rule, just this rule or just this rule, I'm okay. If I use this and keep inferring, I'll get into cycles. And your washing machine isn't exactly doing courses behind your back. It does a few inferences, but it's not exactly doing deep thinking. And so that's fine, is what they were saying. So even incorrect semantics might give you correct results in some special cases, is the best argument that's made there. Okay? So all of this is to get you to say, I won't talk about non-monotonic logics, even though that's one way of dealing with this problem. I won't talk about certainty factors, because even though that's a tempting way, it has problems. I won't talk about fuzzy logic, because once again, it has problems. And I will in fact talk about probabilistic reasoning, which should make you happy because you know it already. You know probabilities. P of A or B. What's P of A or B? P of A plus P of B minus P of A and B. Everybody knew this. You didn't have to take Intro to AI course. Whereas this stuff you didn't know. So I'm just basically going to use what you know already. And in fact, it has more depth. It developed over many, many years. It has clean semantics. There are no circular reasoning issues. So what's the big deal? Now we'll just use it. Okay. So this is a slide that I want you to understand from the point of view of what you know about probabilistic reasoning, this you kind of knew already. One interesting leap that you need to make is essentially a proposition. I mean, you're considering a bunch of Boolean propositions. Okay? And so when I said P of A or B, and you said it's equal to P of A plus P of B minus P of A and B, right? Okay? That's basically because you are talking about probability over multiple variables. Okay? In general, the interesting question is if I have variables A1 to AN, then all the probabilistic queries about A1 to AN can be answered if you know their joint probability distribution. For now, we'll talk about discrete variables. In fact, we'll talk about Boolean variables, even though it can be easily extended to multi-valued variables. And also, probability theory actually also works for continuous variables. We won't talk about them right now. Okay? So we'll look at discrete Boolean variable probability theory. And to answer all questions, all probabilistic questions over a set of n variables, all you really need is their joint probability distribution. Now, if you have, what's a joint probability distribution? It's essentially what is the probability of the world where A1 is true, A2 is false, A3 is true, blah, 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 AN is false. That's one entry. For each such entry, I need to have a number. And all these numbers must add up to 1. That's the whole definition of joint probability distribution. You know this. Before you came, before I start discussing this, you already know this. What I will try to do in this slide is make the connection between what you always knew about joint probability distribution and what you recently learned about model theory for a propositional logic database. They're very connected. Both of them talk about 2 power n worlds, where each world essentially is a truth-falsity assignment over Boolean variables. Right? So in that sense, they're both equal. I mean, they're talking about the same kind of thing, except one gives more information. Okay? So keep that in mind. So model theory for logic. When we did logic, we first talked about model theory, which is the semantics that come from the models. And we understood how to prove theorems from the point of view of models, which is basically writing this big truth table, checking all the models, all the worlds where the knowledge base holds, and making sure that whatever you're trying to prove holds also in all those worlds. That means every world of the knowledge base is also a model of what you're trying to prove. That was essentially theorem proving. And since it takes too much time to do it that way, we learned shortcuts, which is proof theory. Okay? And we made sure that whatever the proof theory does is ultimately justified with respect to the model theory. Remember, this is all we did this. This is not surprising to you, right? So when I go to probability, I'm just going to do the same thing. So I need to understand first what is the model theory for probability and what's the proof theory for probability. You probably didn't think about it this way before, but thinking about it this way makes it much more comparable. The two things that you're learning at the same time. Okay, so model theory for logic is set of all worlds where the formula are the knowledge base holds. And then, so basically given a world, it's either a model or it's not a model. There is no, it's somewhat likely to be a model, somewhat not likely to be a model. It's either a model or it's not, that's it. Okay? In the case of probabilistic logic, for the same word that you're considering here, you give a number between, so in some sense you can say, when it's a word, it's a model, you're giving it like 1, non-zero value, and if it's not a model, you're giving it a 0 value. And all models get the same non-zero value. And all non-models get 0 as their likelihood. That means they're certainly not a model. In the probabilistic logic, in essence, what the joint probability distribution is saying is for each one of these models, it's giving a number, let's say 0.1. Such that when you add up all these numbers, it will become equal to 1.0. Right? Okay? So for each world, you basically are giving the probability P that the formula holds in that world. Your knowledge base holds in that world. Okay? In general, all of the semantics are talking about what does the agent, which has some knowledge, think about which worlds it is living in. In propositional logic case, the agent thinks, these are worlds that I can possibly be living in. These are worlds I'm certainly not living in. In probabilistic reasoning case, the agent says, for each world, I think I'm living in it with 0.1 probability. I think I'm living in this one with 0.2 probability. I think I'm living in this world with 0 probability. I'm living in this world with 0.04 probability. And all these numbers must add up to 1.3. Okay? Okay? So for each world, give the probability P that the formula holds in that world. And PW equal to 0, probability of the world equal to 0, means that the world is definitely not a model. And everything else is a maybe model. And the bigger the number, the more maybe the model is. Okay? That's a way of understanding joint probability distribution. Okay? So, now of course the sum of those numbers should be equal to 1. Okay, now the joint probability distribution has how many numbers? 2 power n minus 1 numbers. Here's an interesting question that I want to ask. If you have n propositional variables, how many possible worlds can you be in? 2 power n. If you have a particular knowledge base, suppose you have your friend, you have knowledge base KB1, your friend has knowledge base KB2, okay, on the same set of propositional symbols. Then if they are different, that's because each of them are saying some subset are models, the rest are not models. Agreed? So how many different knowledge bases can there be from a propositional logic sense? Remember that if I can write large number, 2 different knowledge bases might look different because syntactically different because they have different logical formulas. But they are actually semantically equivalent if they say for every word which is a model for this is also a model for this and vice versa. In which case there is no difference between them. So really the number of knowledge states, number of distinct knowledge states you can have is the number of subsets of these worlds that you consider is your model. That's basically the belief state idea. Right? Number of knowledge bases is the number of belief states. Okay? So the number of belief states is 2 power n. Those are the number of distinct knowledge bases that you can distinguish. Okay? On the other hand, if I now have joint probability distribution, so in the case of probabilistic reasoning, I would say I think differently of the world from you if my joint probability distribution is different from yours. For that to be the case, there at least exists one world for which I give a different number than you do. That's it. That's enough. Then I am different from you. Right? So, here, there are 2 power n dots. Okay? You can give numbers for each of these such that essentially, so let's say this is 0.1, 0.2, blah, 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 0.003, etc., such that they all are positive and they all summed up will be equal to 1. That would be a probability distribution. You can think of this is a 2 power n dimensional real valued vector. Which is actually in this 2 power n dimensional simplex, such that essentially all the coefficients will add up to 1. And each vector is a different joint probability distribution. How many different joint probability distributions do you have?
Infinite.
What?
Infinitely large.
Infinite. Should you be happy about it or not happy about it? So with this, you have infinite number of different knowledge states. So many knowledge states that are distinct here may fall in the same equivalence class here. Which is the reason why you wanted to say, for example, which is the reason why when we were talking about problem in the Pearl case, you wanted to say that if John called and Mary also called, that's somehow different from just John calling. But in the propositional logic scenario, there is no difference. They both fall in the same equivalence class. Do you see what I'm saying? Okay, so in some sense, with probabilistic reasoning, you can distinguish between real minor shades of knowledge. Because there are infinite number of joint probability distributions. Okay, so now if I, of course, were to give one particular probability distribution, if I have to assign a particular probability distribution saying this is my knowledge state, I need to just give 2 power. How many numbers do I need to give to specify my joint probability distribution?
2 power n.
What? 2 power n minus 1. Unfortunately, that minus 1 is not in the in the superscript, but it's at the base. 2 power n minus 1. Why? Because if I give everything but 1, then you can add them all up. 1 minus all of them will be that last one, by definition. Okay? So, providing joint probability distribution, the biggest problem in probabilistic reasoning, which you haven't thought about until now, because you have done probabilities before, but somebody gave you the numbers. Somebody says P of A is this, P of B is this, P of A and B is this. Can you tell me what is P of A or B? And you put in numbers and did an inference. Inference is good. Okay, but the real problem with probabilistic reasoning is getting these numbers. This agent has to make up these numbers. And it needs to make up 2 power n minus 1 numbers. It needs really good imagination to make up these numbers, because that's a lot of knowledge. Okay? So one of the things that's sort of unintuitive, counterintuitive, most of what we did in logic was to talk about how to do the inference fast. We did like a couple of minutes of syntax and mostly spent time on how to do inference fast. In probabilistic reasoning also, we will do how to do inference fast. And before I go forward, do you think the inference in probabilistic reasoning will be polynomial or not polynomial?
Sure.
Do you, for example, see that this column is a strict generalization of this column? You can completely simulate propositional logic in probabilistic logic, but not vice versa. Right? If all probabilities are ones and zeros, then you can simulate propositional logic in probabilistic logic. Okay? And so, this better not be polynomial, because then this is also polynomial. So you expect probabilistic reasoning to be at least NP hard. So that's like a happy thought to get into it. You don't get it any cheaper than NP hard for probabilistic reasoning. And we'll still try to find out how to do it efficiently under what cases. Okay, but the bigger issue is, how do I get these numbers? That's the issue in probabilistic reasoning. The second thing in the propositional logic case is when you have proof theory, so when you had this is the model theory. For the proof theory, what you do is rather than enumerate each of the words that are your models, you just write sentences that you know for sure hold in the world you live in. You'll say P implies A is true in the world I live in. It's true that A implies B is true in the world I live in, you say. And there are many, many worlds where A implies B is true. What you're essentially saying is there are certain worlds where A implies B is false. And you know for sure those are not your models. So every time you write a sentence from your knowledge base, you're constraining the models. We talked about this. In probabilistic reasoning, you make statements like P of A is 0.5. Probability of A is 0.5. Okay? And probability of B given A is 0.7. And furthermore, you make also another very, very interesting kind of statement saying A and B are independent. Why do you care about A and B being independent? Suppose I have your favorite thing. P of A or B is P of A plus P of B minus P of A and B. Turns out that A is 0.7, B is 0.7. Tell me what the value of P of A or B is. Or actually make it this way, 0.5 and 1.5. A is 0.5. Probability of A is 0.5. This is stuff that you know. Probability of B is 0.5. And just tell me what is probability of A or B. To do that, you need this. Normally, what do? You have this, temptation to multiply 0.5 times 0.5 and 0.25. You're allowed to do that only when they're independent. You never paid that much attention to it probably before, but it turns out the independence assumptions are some of the most important things in specifying probabilistic distributions. Because we will see in a minute that there are special cases of probability distributions which can be specified with numbers much fewer than 2 power n minus 1. And the fewer numbers you need, you can get by only if there are more independences that hold. These are called absolute independences. That means probability, this is basically saying probability of A given B is the same as probability of A. That's the independence assumption there. We'll get back to this again. Okay? But there are also conditional independence assumptions that you probably haven't heard of, but here, probability of A given B and C is the same as probability of A given B. Those are called conditional independence assertions. Those are useful because when I gave you extra evidence in terms of C, I didn't really change your belief on A because of this independence assertion. And it turns out those independence assertions are extremely important and they are domain knowledge. Depending on the world you live in, certain things are independent of other things. Right? For example, let's ask the following question. The time this class ends today and what you have for dinner today. Are they independent or not? Well, in many worlds, maybe. But then suppose you're trying to go to a restaurant which is going to end exactly on the dot of 5:45, then they're correlated. Independence, if you say independent, that means those two decisions are completely independent. What happens here doesn't in any way determine what happens here. Okay? And independence assumptions essentially tell us a lot about the worlds we live in. And that's the knowledge about the world. Apart from these kinds of numbers, you also provide assertions of independence between variables and their values. And That's how you really get probabilistic reasoning tractable. Because that way you can reduce the number of numbers you need to give. Okay, let me make that sense, make sense of that in the following way. If I tell you that I have A1 to AN are my propositions, it turns out that they're all independent. They're completely independent of each other. Completely independent of each other. How many distinct probability numbers do I need to completely specify the joint probability distribution? So what I'm basically saying is, let's say I have just A1, A2, A3. Those are my variables. I'm saying they're all independent of each other. A1 is independent of A2, A2 is independent of A3, A3 is independent of A1, and so on. Every pair is independent. Okay? Then I argue that if I just were to give you P of A1, P of A2, P of A3, then I have told you the entire joint probability distribution. Why? Because the joint probability distribution will have 8 entries, right? 2 power 3 entries. One entry would be A1 is true, and A2 is false, and A3 is true. Because everything is independent, this conjunction becomes P of A1 times P of not A2 times P of A3. Okay, not and, these are multiplications. Right? Now, that's basically, if I told you what this number is, let's say this is 0.7, this is 0.3, 0.2, this is 0.3. Okay, then this is 0.7 times 0.8, right? Because P of not A2 is 1 minus P of A2 times 0.3. I give you a number. So instead of giving you 2 power 3 numbers, I got by with just 3 numbers. 3 versus 8 may not be so surprising to you. Okay? If I have, basically 1,000 variables, instead of giving you 2 power 1,000 numbers, I'm getting by with just 1,000 numbers. And if you have to go and assess these numbers somehow, you are extremely happy that you only need to assess 1,000 numbers as against 2 power 1,000 numbers. You see what I'm saying? So if everything is independent of everything, then you just need n numbers instead of 2 power n numbers. And furthermore, if every variable is as likely as every other variable, then I only need 1 number. Right? This is furthermore. But really the big, in addition, if each proposition is equally likely to be true or false, then I just need just 1 number, that probability. So instead of requiring 2 power n numbers, I got by with just n numbers. That's a huge, huge, huge savings. Okay? And furthermore, interestingly, once I have the joint probability distribution, any random query you can ask me can be answered. Okay? What can crazy queries in probability theory be like? I can, for example, ask the following thing. What's the probability that A1 or A2 is true given A3 and not A1? Right? I can answer this. Why? Because there is a definition of conditional probability which you are going to read up before you come to the next class, which says P A and B, P A given B, is nothing but probability of A and B by probability of B. And it's only defined when P of B is not equal to 0. Because we are actually messing around with numbers. And if B equal to 0, then you will start getting infinite probabilities. By the way, when B equal to 0, that means B is false. In first order logic, remember, in propositional logic, if the antecedent is false, anything can be proved. So that is that special case here, except we won't even deal with that. We'll just, don't care about p being 0. Okay, so I can answer these queries too because I know how to answer any of these queries. So I was able to get by with just n numbers. Here's my question. Would you like to live in a world like that? There's a very interesting recursive statement I heard once, which I don't want to believe in because of the course I'm teaching, but it's still quite interesting. It says, if human brain were so simple that it could be understood, we would be so simple that we can't understand it. Did you understand what I'm saying? If human brain were to be so simple that it could be understood, its working can be understood, then we would be so simple that we can't understand it. I don't believe that, because otherwise why am I teaching this course? Right? Right? But that is an interesting quote in terms of what you wish for. You would like to wish for human brain being extremely simple so that I can understand it. But if it is too darn simple, then we would be so stupid that we won't understand a thing. We won't take courses too. We'll have a happy life, but that's a different story. So this is the greatest world in terms of the specification. You just need n numbers. Would you like to live in such a world? Notice that nothing is affecting anything else. That means you have no control of the world you are living in. What are you doing in that world? I mean, unless you are like one of those people, I wish people take care of me, right? And then stop taking care of me when I tell them to. But that also you can't do anymore. Even people who want to be taken care of will once in a while like to tell people, stop taking care of me now. And so they want to affect the world. But if everything is independent of everything, you will be saying, stop taking care of me, and they are not listening to you. They're doing whatever they feel like doing. Okay? If everything is independent of everything, that's not a good world to live in. Just because it's computationally easy, don't wish that to happen to you or your dear friends. So on one hand, you can get by with just n probabilities instead of 2 power n. On the other hand, you can get by with 2 power n probabilities. The question then is, do we always need 2 power n numbers? Well, no. It depends on why should it be that all pairs of things are independent. You live in a world where certain things are thankfully independent of certain other things. If everything is connected to everything, I don't know if any of you are Seinfeld fans. I mean, there was this one episode in Seinfeld where George comes and says the home world and the friend world are colliding. He kept them carefully different, and then somehow they started having interactions. Okay, we want to hope that, for example, if you were, how you do in this course is going to affect your relationship with your boyfriend or girlfriend. That's a little too hard a life to live. You still hope that, you can just crash in this exam and still go and say hello and, have normal time with your boyfriend or girlfriend, or vice versa. So there should be independence. But at the same time, if everything is independent of everything, that's a pretty silly world, because you keep writing stuff on the exam, and I keep giving the grade I feel like, which is what you think I'm doing, but actually not, right? Okay, so there should be dependencies. So what we really want are worlds, more realistic middle ground, where interactions between variables are somehow contained to regions. And so certain subsets of variables are independent of certain subsets of variables, given certain subsets of evidence. So this is George, by the way, when he was saying that his worlds are colliding. I'll send you the YouTube link after tonight. But the point, of course, is if the maximum subset of variables that do actually interact is k-sized, then you just need of the order of 2 power k numbers, instead of the order of 2 power n numbers. And previously it's 0 because k was 0. That basically no variable is interacting with any other variable. You have singleton sets in the previous case. So then the last point I want to make is this, and this will be the first slide again in the next class. You need some compact way of representing independence assumptions between variables. Because we just proved to ourselves that independence assumptions is everything. And there should be some compact way of representing the independence assumptions that you do know. And we will learn as part of this set of lectures, this formalism called Bayes network formalism, which is a graphical model that has both a topology. Not surprisingly, you actually have burglary, earthquake, and John Calling and Mary Calling. There is a topology. The topology of the network tells you what is independent of what given what. If everything is independent of everything else, that graph would be 5 components, 5 disconnected components, no connections whatsoever. And we are saying, by saying this, that alarm really depends only on burglary and earthquake. And if you give burglary and earthquake, then any parents of earthquake and any parents of burglary won't affect alarm anymore. And similarly, John Calling depends only on alarm. If I tell you alarm, then I don't need to tell you about earthquake and burglary, because those are parents' parents. So John Calling gets shielded from these guys by alarm. So you would say probability of John Calling given alarm and burglary and earthquake is equal to probability of John Calling given alarm. Given that, then I need some numbers. The only numbers I'll give you is for each variable, I will just give you the probability that that variable takes a value given its parents take a particular configuration of values. So here there are no parents, so the probability that burglary is true is 0.001. And I don't need to give the false because 0.1 minus that would be false. And here probability of earthquake I gave you. Here for alarm I have to say probability of alarm given burglary true, earthquake true, burglary true, earthquake false, burglary false, earthquake true, burglary false, earthquake false. Those numbers I have to give you. And for these guys I have to give 2 numbers each. John Calling given alarm true, John Calling given not alarm. So by the way, this number is John Calling just like that. Sometimes John calls even when the alarm is not going up. And the number of numbers I have to assess here are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 numbers. Given this topology, I only needed 10 numbers. The moment I give you the topology of the network, you know how many probabilities you need. How many would you have needed in the worst case for this network, for this set of variables? There are 5 variables, 2 power 5, or 32 numbers is what you would have needed. Because of the sparse connections, I can get by with just 10 numbers. If the connections become even sparse, I can get by with just 5 numbers. Okay, this formalism is what we will get to. And the last picture I want to show you is the picture of this guy. Pearl, who we've been talking about, is Hudya Pearl. And he essentially is quite well known in the AI community because he basically came up with the Bayes network representations and proved a lot about it. And many of you may not have known Hudya Pearl, but you know his son Pearl for unfortunate reasons, because he was killed in Pakistan by somebody at some point of time. Okay, but he's probably he's done a lot for the probabilistic reasoning, and that's why we use the Pearl example. Come back next class. We'll hear more about this.